So in the second part of the lecture, let's see a few examples of recursive types. Examples of recursive types. So remember that when you declare a recursive type C, recursive type C with mu alpha dot A, the type system creates a function, two functions for you, fold and unfold. Fold takes alpha C4 alpha A and creates a value of type C, and unfold takes a value of recursive type and unfolds it. So remember that the only way to create a value of recursive type is by applying this fold function. You create the value of this type and apply this fold function. This is the only way to create an expression of type C, a value of type C, a recursive type. So the first example is not actually a recursive type. It's a Boolean type. Data type bool. We define data type bool as either true or false. So how do we encode this data type bool? It's not a recursive type, so we can encode the bool as we have two choices, the left choice or right choice. So with the sum type. And once you take the left branch, then you don't need any extra argument, because the moment that you take the left branch, you know that you will be taking this true value. So there's no interesting content in your choice. So you just use unit. Similarly, unit here. So this is how you encode bool, or how you implement the data type bool in terms of sum type and unit type. Then how do we implement this true? True can be encoded as, you have to create the sum type, so it's going to be injection left or injection right. But true corresponds to the left choice, so it's going to be injection left with the unit, with the annotation unit. And similarly, false can be implemented as injection right unit. So now we know how to deal with the constructors. And what about the destructor? That is, if then else. If expression E, then you take E1, else expression E2. So this expression E has a type bool, and we encode the bool as unit, sum type, unit. So therefore, you just perform case analysis. So case expression E of injection left or injection right. But in this particular case, there's no interesting computational content, so it's just the unit. The argument is just unit, so we don't need actually variable name. So we use this wildcard. In this case, we take the left branch and you evaluate expression E1, and if we take the right branch, which corresponds to the false, then we evaluate expression E2. So this is how we encode the data type bool, which is not recursive type. Now let's see an example of recursive type. So the simplest case is recursive type natural number. So data type nat is defined as either natural number is either 0 or successor of natural number. So how do we encode it? So this is an example of recursive type, because in the middle of defining the data type nat, we see an instance of the type, the very type that is being defined. So it's a recursive type. So how do we define nat internally? We can first start with the equation. natural number is equal to either the left choice or right choice, so you use some type. In the case of left choice, you know that you will use 0, so there's no extra argument. So it suffices to use this unit type. And if you take the right branch, you know that you will be using successor, but there's an extra argument that should be accompanied. So you have to provide this natural number. So you can imagine that there's an equation that governs this recursive type NAT. So this is the equation. And now let's turn this equation into our notation, which is natural number is a recursive type which satisfies this equation, unit plus alpha. So remember that this is some scary notation for solution to this equation, alpha equals unit plus alpha. And that is precisely solution to this equation. So this is how we encode the NAT, recursive type NAT, using this recursive type notation. Now, how can we encode this 0 and successor? Remember that when you declare this recursive type NAT, the type system automatically creates two functions for you. The first is fold, and the second is unfold. So fold takes unit plus NAT and then fold it to create NAT. And unfold takes NAT, natural number, and then unfold it. So it returns unit plus NAT. Now we are ready to encode everything. First, how do we encode 0? Remember that 0 is of type NAT, and the only way to create a variable type NAT is by applying this fold function at some point. So you have to first prepare an argument, this one. And in the case of 0, you take left branch. So you have injection left of NAT, and there's no interesting argument, so it's unit. So this one has a type unit plus NAT, and now it's a matter of applying the function fold NAT. Then the whole expression is going to have type NAT. That's how we encode 0. What the successor of an expression E? So this time, this expression E has a type NAT, and the whole expression also has a type NAT. And in order to create a NAT, you have to eventually apply this fold function. So you have to apply this fold function, and the argument should have a type unit plus NAT. And in this case, we take the right branch, so injection right with this expression E, and the annotation is a unit. So that's how we encode this 0 and successor. So now we have dealt with the two constructors. What about the structure? That is, how do we encode this case analysis? Case expression E of, if this is 0, so expression E has a type NAT, and if it is 0, then we evaluate expression E1. And if this is successor of some x, then we take this expression E2. The question is, how do we encode this one? So we have to first unfold this NAT to see if it is injection left or injection right. So what we do first is apply unfold NAT to expression E. Now this guy has a type unit plus NAT. Now we are ready to perform case analysis on this sum type. So if this is injection left x, then we created this natural number, this net, by taking the left branch. In this case, the content, the argument is uninteresting. So we take this branch and we keep evaluating expression E1. If not, we have previously taken the right branch, that is, we created this natural number with this successor construct. So in this case, this is going to be injection right, and this x is going to be this variable, this pattern variable x. So this variable x is going to be bounded to the actual argument to this success construct. And then we evaluate the expression E2. So it's just, once you apply this unfold function, it's just an ordinary instance of case analysis on some type. The only difference is you have to first apply this unfold function to turn this recursive type net into this sum type. And similarly, you can define, for instance, data type and natural number list, which is nil or cons of natural number list. So in this case, natural number list can be thought of as a solution to the equation mu alpha dot. It is either left side, which has no interesting argument, or the right side, which corresponds to this one. And in this case, you have to provide natural number paired with natural number list. But we don't write the natural number list because we are inside this new notation. So it is alpha. And similarly to the case of recursive type net, you can actually implement nil, cons, and the pattern matching on natural number list. So this is how you actually implement the recursive types. And basically you want to implement this idea in your programming assignment 7. And the course notes gives an interesting example where the recursive type does not have actually some type. So in this case, the recursive type actually uses this sum type. This n list uses this sum type. And in the case of this natural number, you also use a sum type. But this sum type is not strictly necessary in creating recursive type. So for instance, we have this recursive type, data type, natural number stream. Stream is the type for, basically stream is infinite list. Infinite list. But you cannot actually store this infinite list in memory because you are going to run out memory. So instead you have to describe how to generate every element in this infinite list one after another. And the only way to describe this process is to create the function. So the conventional way of implementing streams in function programming is to create the function that generates the elements, individual elements. So the data type natural number stream is defined as construct a natural number stream of type unit arrow net times net stream. So what this thing means is that we want to actually encode infinite list of natural numbers, but there's no way to store an infinite list of natural numbers in memory. So what we do is we instead created this function, and this function, when applied with the argument unit, it returns the first element in this stream, and the remaining stream. So for instance, if you have an infinite list of natural numbers 1, 2, 3, 4, blah blah blah, then when you apply this stream, the function with the argument unit, then you are going to get back this 1, the first element, and the remaining stream 2, 3, 4, blah blah blah. So this is a type n stream. And after applying this function to unit, then you are going to create this net and the remaining stream. So this is a recursive type because in the definition of this type n stream, we make reference to the type that is being defined. So this is an example of recursive type that does not use some type. So basically n stream is solution to this equation mu alpha dot unit arrow net times alpha, and here there is no sum type. So the lesson here is that sum type is not some the lesson here is that it's not required to use sum type in the definition of recursive type, as exemplified with this natural number stream where we don't have sum type.